Hey guys, hello everyone. So this is another video for the previous year questions on the organic reagents and name reaction basically. So we are here, we are going to discuss questions from June 2018 and December 2018 in this particular video. So let's start guys. And also if you still haven't subscribed to the channel, please do, because many such nice videos are coming up. Also, let's start with the first question, guys. Do solve the question by yourself and then see the solution. Okay, so the major product formed in the following reaction is, the molecule is indole and you are taking lithium in liquid ammonia in the presence of methanol, which is going to be a proton donor, proton source. All right, so the question is of selectivity. This is Birch reduction, very simply. Alright, Birch reduction. So guys, what are you going to do? Where are you going to transfer the electron from the alkali metal? Absolutely to the more electron deficient ring. So this ring is the more electron deficient ring, and such that the electron should be transferred such that you are not getting the direct electron density in the 5-member ring, because otherwise it will be very unstable. So the electrons is transferred in such a way that you get the negative charge as far apart as possible. The 5-member ring does not have the electron density directly. Yes, all right, resonance may take place, that's not a problem, but the electron density should be as far apart as possible. And after several steps you are going to get this product reduction over here. All right, you can follow the mechanism of Birch reduction. Very simple. Your answer is option number 4 for this particular question. Very simple, guys. All right, another question from June 2018. Once again, the major product A and B formed in the following reaction sequence are. So as you can see, you have a ketone and the aldehyde group in this particular molecule, and then looks like you're having a stable ylide over here. What is a stable ylide? A stable ylide is basically having a negative charge on a carbon having an electron withdrawing group. Alright, so this is your stabilized ylide, which can cause resonance. Alright, so stable ylides are particularly observed. They are going to absolutely react with the more reactive aldehyde group, and they are also seen to give the E-alkene as the major product. So you are going to get the E-alkene or the trans-alkene as the major product. If we want to write the structure of the product directly, this is your Wittig reaction, and a stable ylide is going to give you the trans-alkene. First reaction is Wittig olefination, yeah, Wittig reaction, formation of alkene from the aldehyde. What about the second reaction? The second reaction is CH2 double bond CHOET. This is along with heat. So looks like this is going to be a, alright, now there's a double bond missing in the question. Right, there is a double bond missing in the question because the second reaction, this is a 4+2 cycloaddition, and we also have particular options in the question, right? So we are going to just see, in this way you can just directly cause the 4+2 cycloaddition reaction. Okay, and if you just focus on the stereochemistry, both of these hydrogens are on the same side, they are pointing on the same side. Okay, and always whenever you take these kind of groups, the ester as well as the OET, they are going to have a secondary interaction and both of them are going to go endo. Alright, both of them will be endo. The selectivity going to form a 6-member ring. These two hydrogens, if we are supposing that they are going to be above the plane in this way, then the ester has to go below, and also following the endo rule over here, the OET group also goes below. Alright, so the product is going to be option number 3. First reaction is a Wittig reaction, E-alkene obtained by a stable ylide having an electron withdrawing group. Second reaction is 4+2 Diels-Alder reaction. Okay, we move onwards to next question, guys. So the structure of intermediate A and the major product B formed in the following reaction are. Now this is a very direct reaction which has been asked. All right, and I think that you can very quickly say which reaction is this. It is Bergman cyclization. And guys, it is a radical reaction, absolutely. So what are you going to do? You have studied this mechanism very recently. In the presence of heat, the molecule, the ene-diene system, what is it? It is ene-diene system, is going to open up, and it is going to form a bond like this, a double bond. One radical will be over here, another radical is used up for the formation of a single bond, one more radical over here. So you are getting the 1,4-di radical in this way, and in the presence of a hydrogen or a deuterium source, it is going to abstract the deuterium, and the final product is going to be 1,4-dideuterium in this case. Yes, this is your benzene molecule that you obtained, and on the 1 and the 4 position you are going to get 2 deuterium atoms. Okay, so this is a very simple reaction, Bergman cyclization radical reaction, asked in June 2018. So basically guys, June 18 paper has plenty of good questions and also very easy and repeated questions, as you will see. The major allylic alcohol A and the ester B formed in the following reaction sequence are. So the first thing that you see a tosyl hydrazone, and then you see two equivalents of butyl lithium. You are absolutely going to think about the same name reaction which we have done plenty of times in all of these papers, Shapiro reaction. Yes. So you are going to, in the presence of two equivalents of butyl lithium, you are going to remove this acidic proton first, which is there on nitrogen, and then you are going to remove this proton. So what do you get? Let's say this proton is removed and you can remove the tosyl group from over here. So in this way you're going to get a double bond, and nitrogen nitrogen double bond, and one minus charge on this particular nitrogen minus a tosyl group. So this is what you have. Further elimination of nitrogen gas will give you a carbanion basically on the sp2 carbon. Okay, so this is your carbanion, followed by, you also have an electrophile guys, but the electrophile is only formaldehyde. So if it attacks on the formaldehyde, you are going to get the alcohol. You're going to get this kind of an alcohol. What is this? Allylic alcohol, absolutely. So this is your allylic alcohol. Where is the double bond? From where? From which side the proton has been removed? Now the question is, the proton could be removed from this side also, right? Yes or no? The proton could be removed from here and the proton could be removed from here. Both the sides it is available. Second thing is guys, butyl lithium is not a very bulky base, I would say, but yes, it is bulkier than OH minus and methoxy and so on. And also it is a very stronger base. So stronger base is going to be very less selective. So what is it going to do? In the Shapiro reaction guys, always understand, in the Shapiro reaction, when there is a possibility, you get the less substituted alkene. Okay, and if it was the Bamford-Stevens reaction, you would rather get this product. Okay, in the Bamford-Stevens reaction, you might have got this product, but in the Shapiro reaction, having a stronger and less selective base, you have this molecule. Okay, alright, so A is absolutely wrong and 4 is also absolutely wrong for this. Now what next? Alright, so let's erase everything. Let's write the next step. So yes, you have got the allylic alcohol in this way from the less hindered side in the Shapiro reaction. Okay. Now next thing you see, there is a orthoester. Absolutely guys, as soon as you look at the orthoester, and that also in the presence of propanoic acid or any other acid, you are going to first of all think of the formation of allyl vinyl ether. I'm directly doing this step because it has already been done in one of the mechanism videos. So this is what you are going to get, the allyl vinyl ether system. Alright, yes, the allyl vinyl ether system. Also, when you are having oxygen inserted in between 1,5-diene, this is going to qualify for a Claisen rearrangement in the presence of heat. Which Claisen rearrangement is it? Let's see. If it is going to give you, it is going to give you an ester. It is going to be known as Claisen ester condensation. No, not at all. Johnson rearrangement. All right. So this is going to be Johnson Claisen rearrangement. Yes, guys, you have different names for 3,3 sigma tropic reaction. I have made a video which is having plenty of uh, name reactions on 3,3 sigma tropic. You can just check it out. So this is going to be your product. All right. Yes, absolutely. This is going to be the product, and the reaction is Johnson Claisen rearrangement. Yeah, also there's a misprinting over here. This is a single bond, and this is also a single bond. So what is wrong in 2 and 4? What is the correct option? Correct option is 2. What is wrong in 4 is this methyl is not coming up over here. There is no possibility that the methyl will come here. Okay, so the 4 is absolutely wrong. Only one minor silly mistake you could have done, but you have to be very careful. This is your product option number 2. Alright, moving onwards to another very nice question. Question from again June 2018. The major product A and B formed in the following reaction sequence are. So when you see vicinal diols, alright, you might think of pinacolon rearrangement, but here you are using tosyl chloride. That is, you are going to do the tosylation of one of the alcohol. Which alcohol are you going to tosylate? That is the question. What is the difference between two alcohols? One of them is a secondary alcohol and the other one is a primary one. So primary one is absolutely the less hindered one. So what you are going to do is, in the presence of acid, or let's say pyridine base, you are going to tosylate the primary one, less hindered. All right. Second step is basic medium. CaCO3 is only a mild base. So in the presence of a mild base, you are going to eliminate this proton from here, and the ring has to expand in this way. And since the tosylate is a good leaving group, the ring can expand. Okay. So after the expansion, this carbon-carbon bond is going to come up over here. Alright. So it is going to form a 7-membered ring system. This way. Alright, something like this. It's going to first of all form a 7-membered ring system, followed by what do you have, guys? You have a sulfonium uh, cation, and in the presence of a base NaH, a proton could be removed from here. Alright, you might have this kind of a sulfoxonium ylide system. But guys, you are in the Korechkovsky reaction, you have two possibilities. Either you do the cycloaddition, that is the cyclopropanation, or you do the epoxidation. There you only have one possibility, even though it is sulfoxonium one, the more stable one, right? But you still have only one possibility. Since there is no carbon-carbon double bond, it's only going to lead to epoxidation. Alright, the first reaction is your semipinacolon rearrangement, and the second reaction is Korechkovsky reaction, epoxidation. Alright, next important question is from December 2018. Yes, very very important, guys. The major product formed in this following reaction is. Now this reaction is a little bit different from the usual reactions that we do. What do we call this? We call this a Kulinkovich reaction. Alright. So this reaction is basically a cyclopropanation reaction only, with a little bit of rearrangement taking place over here. So what are we going to do about this? First of all, you have the reagent titanium isopropoxide. So let's look at the mechanism, guys. Titanium isopropoxide whole 4. You can draw it in this way. Alright. So the ethyl magnesium, the negative charge on this carbon, it is going to attack over titanium and it's going to remove two of the isopropoxide groups. Okay, so the titanium molecule finally becomes in this way: CH2 CH3, one more CH2 CH3. All right, now from here you are going to do minus methyl methyl, that is minus of ethane. Elimination of ethane from here is going to result into this kind of a metallocyclopropane formation. Okay, yes. Now what happens, guys? You are having some ester over here in the molecule. Yes, so I'm just writing this ester as RCOOME, and this whole cyclohexyl group is R, and this is methyl only. So I'm writing this whole group as RC double bond O OMe over here. What happens is the carbonyl is going to attack over titanium and one of the bond is going to fall over this carbon. Alright, and you get a typical intermediate which is going to be, I guess, a 5-membered ring. Let's see. Right, titanium, isopropoxide hold twice, one carbon already present, second carbon, third carbon, fourth is your oxygen which forms a bond with titanium. Absolutely. So you are going to get this kind of a molecule. You have OMe and you also have the R group. Okay, so this is your 5-member cyclic system over here. Followed by this, I see that I have a good leaving group. Now this oxygen is a good leaving group since it has the titanium, right? So I'm going to directly lead to this product. All right. Yes. So, all right. So what did you get, guys? Acha, sorry. This methoxy is going to eliminate when this attack is taking place. Just 1 second. Also have to remove the methoxy before we do anything else. So when the attack takes place, the methoxy is going to get eliminated. So what do you get? You get a 3-membered ring R, and this becomes O, and the oxygen is going to still have the bond with titanium. OTI, isopropoxide hold twice. Okay, and after the hydrolysis, after the acidic workup, finally you are going to remove this oxygen titanium bond and you get this kind of an alcohol. All right, and the minor product is EiO isopropoxide hold twice. Now what do you get in this molecule? Particularly you have the R group as it is, so this is your R group as it is. You have this 3-membered ring as well as the OH. Alright, so answer is option number A. This is your Kulinkovich reaction. Okay, Kulinkovich reaction, very easy. Now move on to this next question, guys. The major product formed in the following reaction is. So you can identify this question by yourself. It is again very simple. It has been done very recently. Yes, what is this reaction? You have alpha sulfonyl alpha thioalkane, the carbonyl basically. This is a rearrangement reaction, guys. As far as you can recall, this is a Pummerer rearrangement reaction. Alright, it is a Pummerer rearrangement reaction. And what are you going to do? First of all, metachloroperbenzoic acid is going to cause the heteroatom oxidation. I'm directly writing it over here only. The first step, one equivalent metachloroperbenzoic acid gives the heteroatom oxidation. Now this heteroatom, it is going to attack on the acetic anhydride in this way and get you this molecule, the carbon. Alright, still there is a positive charge over here. Now since there is a positive charge on sulfur, also the sulfur has a good leaving oxygen group now. What do we talk about this proton? Is it going to be very, very acidic because there is a carbonyl and then there is a sulfur? Absolutely, it is very acidic. So the acetate which has removed from here is going to take away this proton very quickly. And after the proton is removed, what are you going to do? Alright, after the proton is removed, you can basically write the molecule in this way. Okay. So the negative charge falls over sulfur and the whole group is going to leave because it is having a good leaving group, the acetate, right? And you are forming some kind of a chloro. You're going to form some kind of a sulfonium ion, isn't it? Yes, double bond S and pH and a positive charge on the sulfur. Alright, what about the next step, guys? The next step is you have still got the acetate which is free. Yes, this acetate got free. Where is it going to attack? On this position. OC double bond OCH3. This is your rearrangement reaction basically. Why? Because in the first step you have got sulfur only, and in this last step you see that you have a acetate group connected on this carbon. Now final step is Na2O3 Na2CO3. This is going to be the hydrolysis. Now where is the OH minus going to attack? If it wants to do hydrolysis, the OH minus will attack over here and it is going to open up this bond. Once it opens up this bond, as you can see it is opening up this bond, you can directly remove the thiol, isn't it? You can directly remove the thiol and you will have one more carbonyl over here. So the answer should be option number D. Okay, so this is fumarate rearrangement and this is your mechanism towards the fumarate rearrangement. Very, very simple reaction. Now the last question that we do in this session is once again December 18 paper. The major product A and B in the following reaction sequence are. So first thing guys, you're having a dihydropyran molecule and reacting this with CCl3 COCl. Alright, CCl3 only and COCl. So what are you going to do guys in this particular molecule? Let's say we draw the molecule in this way so that you can consider the elimination. In the presence of zinc and copper couple, you know what is going to happen. Zinc is going to transfer the electrons and it is going to give you a dichloroketene molecule, isn't it? Dichloroketene. And the dichloroketene is going to react with this carbonyl. Okay, you have got 2Cl over here, one carbonyl on this side. Let's say you have got this product. Okay, right. Now, why this particular selectivity, guys? You can break down the molecule, you can try and form radicals. The possibility which is going to give more stable radicals is absolutely this one. Alright. And lastly, metachloroperbenzoic acid. Now here you don't have to do heteroatom oxidation because here you already have two oxygens into the system. Also what you're going to do is you are just going to do the Baeyer-Villiger oxidation, right? So the Baeyer-Villiger oxidation, guys, where is it going to take place? To the side which is more electron rich. The oxygen will be transferred to the side which is more electron rich. Alright? Yes, absolutely. The more electron rich is going to be this side. Alright, so this is your final product which you have got, and the answer is option number D for this question, right? Specifically this regioselectivity this way combination, because you are going to get stable intermediate in this case. Alright, stable system you are going to get, and the second one is just Baeyer-Villiger oxidation. Alright, so guys, I think that you have seen quite good questions today, and if you are liking this session, please don't forget to subscribe to the channel. I will see you in another such video very, very soon. Bye everyone.